Hello everyone and welcome. My name is Kanishk Zaman, and on behalf of our team, I'd like to welcome you to the final presentation of LocalLens. It is a high-performance multimodal retrieval or augmented generation system for local document intelligence. With me today are my teammates Arman Chaudhary, Arjun Saxena, and Kartik Nagar. This project was built under the guidance of our mentor, Professor Sushmita Das at Bennett University. LocalLens is a result of months of engineering, problem solving, and a genuine belief that AI tools for sensitive data don't have to compromise on privacy, accuracy, or user experience. It is our April 2026 final submission, and we are proud to present it to you.
Before we dive in, here's a quick overview of what we'll cover. We'll start with the problem that motivated this project, then walk through our four core objectives. From there, Arjun will take you through the system architecture and the retrieval engine, the beating heart of local lenses. Arman will cover the ingestion pipeline and the workspace design, showing you how the system sees and processes your documents. Kanishk will then explain our privacy and trust features, including the local LLM and our hallucination detection system. I'll close out with the technology stack, our team's work division, and our conclusions. We have tried to make this presentation reflect the system itself, precise, structured, and built with care. Let's get started.
Okay, so let me paint a picture of the problem. Imagine you're a lawyer reviewing thousands of pages of sensitive case files, or a medical researcher analyzing confidential clinical data, or an enterprise team working with proprietary product documentation. In all of these situations, the data is sensitive. It cannot leave your organization, but the AI tools that can help you work faster, find answers, and surface insights. Almost every single one of them is cloud based. The charts, the figures, the diagrams, which are often where the most critical information lives. On top of that, these tools typically use a single retrieval method, which leads to poor accuracy. You ask a question and get back something that sounds plausible but misses the mark. Local Lens was built to solve all three of these problems at once: the privacy gap, the multimodal gap, and the precision gap. Every design in Local Lens traces back to four objectives. The first is data sovereignty. No data ever leaves the local machine. Not during ingestion, not during retrieval, not during generation. The entire AI lifecycle runs on your hardware. The second objective is multimodal intelligence. We believe that ignoring charts and diagrams in a intelligence system is like reading a book with half the pages turned out. Local Lens treats visual element, every chart, every figure, table, and diagram, as a first-class citizen in the index, equally searchable as any piece of text. The third objective is hybrid accuracy. We knew from the start that a single retrieval method would never be good enough for diverse real-world documentation. So we engineered a system that runs multiple retrieval strategies in parallel and fuses their results mathematically. The
The architecture of local lenses is built around three clean layers, and I'll walk you through each one. At the top, the front end is modern React 19 application built in TypeScript. We designed a custom high-end monochrome glass morphism interface. It's not just aesthetically distinctive, it's functional. The dual pane workspace allows you to ask questions on one side while the exact source reference, text or image surfaces on the other is in real time. Answers stream token by token using server sent events. So there's no waiting for a full response to load. In the middle, the backend is a fast API service in Python 3.11. This layer orchestrates three things: a parallelized document ingestion engine, an AI layer that manages both the local LLM interference and the clip embeddings model, and the hybrid retriever, which fuses results from multiple search engines using reciprocal rank fusion. At the base, the data layers is a combination of three purpose-built databases. Uh, Milvus handles high-dimensional vector embeddings for both text and images. PostgreSQL manages all relational data document metadata, chunk references, and persistent that persistent chat sessions. And MinIO provides local S3 compatible object storage for raw documents and extracted visual crops. The key architectural principle throughout: nothing in this stack requires an internet connections. It's fully self-contained and fully private.
Right. So my primary responsibility was the ingestion pipeline, specifically the visual intelligence side of it. And I want to walk you through what actually happens when you upload a document on LocalLens. The text side goes through sentence-aware chunking using custom digits splitting, which preserves grammatical context so that retrieved chunks actually make sense to the LLM downstream. Finally, every document gets an MD5 hash stored in PostgreSQL to prevent reingestion of duplicates. The entire pipeline runs in parallel threads, multiple pages are processed simultaneously, so even large document index quickly. The result is a rich, unified index where every word and every visual document is found in.
Okay, this is the section I'm most excited to talk about because the retrieval engine is what separates LocalLens from every other local RAG system. Ranked result lists. We apply reciprocal rank fusion. RRF is a mathematically principled algorithm that scores each document chunk based on its rank across all retrieval engines, not just its raw relevance score. This means a chunk that appears in the top results of all three engines gets a very high fuse score, even if it wasn't the top result in any single one. The system also supports dynamic session scoping, so retrieval is always filtered to your current document set, and it injects the last five messages as context so follow-up questions work naturally.
Okay, so let's talk about privacy and trust features. As it was previously mentioned that my domain was AI reliability, making sure that local lens does not just answer questions, but that users can actually trust those answers. Let me start with the inference layer. We ran a quantized 4-bit Qwen3 8 billion GGUF model locally via Llama CPP Python. Quantization allows us to run a genuinely capable large language model on a consumer hardware without requiring a data center. Inference is entirely local, no API calls, no network access. Before loading the model, we perform a RAM availability pre-check to ensure the hardware can handle it stably. Answers are delivered via a server-sent event, streaming token by token, so the experience feels live and responsive. We also automatically filter out reasoning tokens, the internal chain of thought artifacts, some model that emits, so only the clean and the most final answer reaches the user. Now, the part that I am most proud about, the trust layer. Hallucination is the core problem with generative AI.
And I wanted to explain the thinking behind it. Because the UI wasn't designed to look impressive in a demo, it was designed for people who spend hours working inside of it. The core experience is a dual pane workspace. On the left, a persistent Q&A chat interface, and on the right, a document reference sidecar panel that updates in real time as you ask questions. When the system cites the source, the exact passage or the exact visual prop appears in the sidecar, so you never have to leave the interface to verify an answer. If the cited source is a chart or diagram, you see an actual image prop rendered inline inside the chart flow. This is the multimodal experience end to end, not just in the pipeline, but in how the information surfaces to the user. The design system is what we call high-end monochrome, built with tailwind CSS, glass morphism effects, and desaturated panels with lucid icons for consistent minimalist design systems.
So let me give you a complete picture of technology stack. Because the choices we made here weren't arbitrary. Each one was selected to serve a specific requirement. On the AI and ML side, Qwen 3 8B for local element preference via Llama CPP Python, Clip VIT B32 for cross-model image embeddings, sentence transformers with mini LM-L6 for dense text embeddings, Tesseract OCR for scan documents, and OpenCV for visual layout analysis. On the backend, Python 3.11 with fast API for the service layer, LangChain for prompt orchestration, and rank BM25 for sparse keyword retrieval. On the front end, React 19 with TypeScript White as the build system, Tailwind CSS for the design system, and Lucide icons for iconography. The data layer is Milvus for vector storage, PostgreSQL for relational metadata and session management, and Mini IO for local object storage. Infrastructure is entirely Docker and Docker Compose. The full stack launches with a single command via our run.sh script. We also ship a resetdb.py utility for clean slate reinitialization and a full playwright end-to-end test suite covering the onboarding and querying paths. Every library in this stack is open source and run entirely offline.
Hmm. Again, I'm Arman. I own the visual intelligence domain. My work covered the full OpenCV region detection pipeline, the clip embeddings integration, the image search UI in the front end, and the end-to-end multimodal indexing workflow that ties the visual pipeline to the retrieval engine.
I'm Arjun, and my domain was retrieval excellence. I built and tuned the BM25 keyword search engine, the reciprocal rank fusion logic that merges all three retrieval modes, the sentence aware chunking and algorithm, and the precision answering rendering on the front end.
Okay, so I'm Kanishk, responsible for AI reliability. I handled the LLM inference integration with Qwen3 via Llama CPP Python, designed and implemented the hallucination checker with percentage support scoring, and built the verified citation UI that displays score confidence to the user.
And I'm Karthik. My domain was systems architecture. The foundation everything else runs on. I designed the PostgreSQL scheme with foreign key integrity across documents, chunks, and sessions. I built the session management system, orchestrated the Docker Compose infrastructure stack, and developed the ingestion UI, including the terminal style processing log. We used a vertical slice over ownership model. Each of us owned a complete feature from the user interface all the way down to the database layer.
एक सेकंड कंक्लूजन नहीं कर देता हूँ
Thank you वाला part मैं बोलूँ.
तेरे को कंक्लूजन करने कर ले आंसर ठीक है
Okay, so it is about the conclusion and a big thank you. So what has actually LocalLens demonstrated? It has demonstrated that a protection-grade, privacy-first AI document intelligence system is entirely achievable without cloud infrastructure. We have built a system that rivals commercial cloud alternatives in both capability and user experience, while offering something they fundamentally cannot complete, complete data sovereignty. Every document stays on your machine, every answer is verifiable, every visual is searchable, and the entire stack launches with a single command. We believe LocalLens is more than a student project. It is a blueprint for how private, trustworthy document AI should be built. Thank you to Professor Sushmita Das for her mentorship and guidance throughout this project. And a very big thank you to everyone watching. We'll be happy to take your questions.